My name is Nerea Marcaide, and I am the coordinator of the AIRPOXY project. On behalf of the entire consortium, I would like to welcome you to this workshop that we have prepared with such enthusiasm. AIRPOXY project was born to contribute towards maintaining the leadership in the European aeronautics industry through the development of new innovative materials and tools for novel composite materials. In addition to presenting the results of the project, today we will have the opportunity to learn from the hand of great experts the latest trends, challenges and opportunities that are being developed around the composite materials in the aeronautical sector.
Thanks a lot to CDTech and Elena especially for giving me the opportunity to present specific polymer work in this area. So today's talk is about chemical design of sustainable resin for build-to-spec thermoset materials. But before going a bit deeper in this subject, I would like first to give you some more input about the company and what we are, because I think it's important to understand where we are in the supply chain. So first about our activities and skills. So Specific Polymers is a SME company. We are 27 people. Mainly acting as a research and development service providers for industrial partners and in the scope of collaborative projects. And so we design new materials with the idea to validate proof of concept. So we are really at the bottom of the value chain, trying to define new materials for the future. So we are working worldwide. We are selling products all over the world. It represents approximately half of our turnover. We are selling products, but mainly the main part of our turnover is based on the selling of research and development projects. So this is our skills. So at the early beginnings, the activity of the company was geared towards the synthesis, the ability to synthesize custom designed polymers with very specific functionalities. And so I would say that about 80% of the molecules that we are proposing in our R&D portfolio is products that are not sold anywhere else. So it's not really interesting it's only interest very specific area, a few people in the world, but we are the only companies that are selling these products. So polymer synthesis at the beginning, and time by time, because we needed to go closer to the market, we developed a formulation of resin activities, and the idea was to, based on our understanding on the chemistry of the resin, fully design a resin formulation that is consistent with the specification linked to the implementation processes and linked to the final applications. So it's really designing the formulation to reach objective and not bring a formulation with its own specifications. Design off is just to mention that we can take a project since the early beginning, defining strategy to push forward at the experimental part, and physical chemical characterization because we are characterizing all the products and all the things that we are doing. And industrial transfer, it's an activity that is getting more and more important in the company, because each time when we are developing a new molecules, a new polymer that is interesting, the next question from our customer is, okay, it's interesting, it's give good property, but what next? And what next? We need to produce it, and we need to find a way to produce it. So we are working more and more with tool manufacturers in order to transfer to them our synthesis process, optimize them, in order to produce at first 1 kilogram and then 25 kilogram, and then give enough matters to validate the proof of concept in some applications. So this is what we do. In which areas? So we have 4 main areas: high performance materials. So it's mainly dedicated to aerospace and aeronautic applications, because as it was mentioned today, we need to get composite material which has lightweight but can compete with metals in some applications, so in some hot wet zones. So you need to have some resin with very high thermomechanical resistance. So it's what we are trying to do. Also, we are working in some specific coatings with some specific hydrophobicity, or oleophobicity, or conductivity, because we need to solve out some issue also in this area. We have more and more work at the moment in the field of energy, mainly lithium batteries. developing a solid polymer electrolytes in this area. Environment, I think I will go deeper in the next slide, so I will not talk now about that. And the last part is health. It's more, I would say, for the moment, it's not something we pushed for the moment. It's more an opportunity because we are able to design some specific polymers. But it's something we would like to develop in the future. So now going deeper on the main subject of this talk, so chemical design of sustainable resin for build-to-spec thermoset materials. And to start explaining what we are doing in this area, I wanted to show some slides about the current situation and where we are now, which explain what we are trying to do. So it's somehow give some echo to what Philippe Christou explained this morning. So at the moment, in the field of epoxy, as you may know, 80% of the resin are based on bisphenol A diglycidyl so epoxy resin. It's aromatic, it gives good properties, good chemical resistance, it's low cost. So I would say, apart from the sustainability aspect, it's perfect. The second resin that is interesting in Novolac-based epoxy resins, so it's the one that is the oligomeric one that is here. So it's also interesting in terms of properties. Then in a lesser extent, you have cycloaliphatic epoxy resins that are used in some application, for instance, for avoid any yellowish of epoxy resins. And then you have other kind of aliphatic epoxy resins that are used and formulated with the others to adapt the properties and give interesting formulations. So this is where we start, but it has some issue. It has good property, but it has some issue. It's synthesized from various compounds that are toxic and damage the environment. So epichlorohydrin, it's highly toxic and classified as substance of very high concern. If we speak about epoxy Novolac, it's based on phenol and formaldehyde, which are also very toxic compounds. And finally, if you want to make bisphenol A diglycidyl ethers, it's based on bisphenol A, which is very harmful. And as it was explained by Caroline earlier, it's something that we need to try to figure out to propose something else. So this is the point, the toxicity. Then most of it is petro-based at the moment. So we need to find alternative feedstocks. And finally, as we all know, and I think it's the main subject of the day, thermoset resin are not recyclable at the moment, and we think we need to find alternative to consider the end of life of such materials. So the forcing solution at the moment, and it was also explained this morning, it's epichlorohydrin, and its brand name Epicerol can be bio-based. So now it can be made from natural glycerin and hydrochloric acids. So it's a way to obtain partially bio-based resins. So this was explained this morning. And a second aspect, you have different kind of aliphatic epoxy resins that are based on paper or sugar industry, biofuel industry, or for food industry that can give epoxies and can be used as in resin formulation in order to increase the bio-based content. But the problem is these resins are low performance because aliphatic, and so you cannot push them too fast, too far, because if you want to reach higher performances, they are not consistent. So this gives somehow the point where we start, what we want to do. So the problem is GBA is still the main component, and we need to find an alternative. Okay, it can be bio-based, but for the moment it's mainly based on Epicerol, and even if it's bio-based, it's still toxic. And with this solution, as it was also explained, we can only reach bio-based content from 29 to 66%, which is not that high at the moment. And I mean, it's good to have that already, but we need to go further. So within specific polymer, we are focusing on I would say the core of the epoxy, so the phenolic or the alcoholic compounds that we use to make epoxies, and we are focusing at the moment on derivative from sugar or from lignin, and I will explain a bit later. So our whole strategy is based on this I would say, value chain or all steps to make a material. So first, we really consider the raw materials, trying to figure out what is the most interesting biomass that we can convert into epoxies. And I will explain what is the main criteria that we are taking into consideration to select these raw materials. Then in our chemical processes, in order to make the epoxy out of these precursors, we are trying to use green chemistry principle to have eco-responsible approaches. And then we are also thinking at the early beginning of the conception of the material of impart into this material reversible bonds in order to achieve 3 art properties that it was explained today. So this is our strategies. So if I go back on the selection of the precursors, so the main aspect we are taking into consideration when we select some precursor from natural resources is first their naturality, of course, their chemical structure. What we want to do is to have I would say, a range of properties from low TG to I hope high TG in the future. And so we are selecting aromatic, aliphatic, cycloaliphatic compounds in order to have this variability. And also in terms of physical property, you need some molecules that are viscous, you need some molecules that are very liquid, and play with them in order to make a suitable formulation. So this thing we can tune at the early selection of the chemical structure. We also have a look on the access of these resources and abundancy, because it doesn't make sense to develop a full resin on a precursor that cannot be produced in sufficient volume for the application that is considered. And of course, we also look at the toxicity. And then when we have identified the precursors, the objective is to convert them into epoxies and time by time go to a production of at least 30 kilograms in order to achieve some test. So this is some chemistry. I'm sorry, but I need to show chemistry of the main precursor we developed in the past, and we made a differentiation in between sustainable epoxide and bio-based epoxide. So what we call sustainable is we know, or we are pretty sure that it's interesting alternatives that can be bio-based in the future, or that the supply chain to have it bio-based in the future is already starting to be developed. But for the moment, what we sell, it's petro-based. But at least it's not JEBA and it's not toxic. So for the moment, it's what we sell, sustainable epoxy. So it's based on vanillin alcohol, it's based on fluoroglycinol, resveratrol. So this is all aromatic phenols that can be extracted, for instance, from wine residue or for algae. And we convert them into epoxy, and we work on the chemical synthesis in order to have something relevant for pilot scale. And then we have some bio-based epoxies from isosorbide, for instance, which is this cycloheteroaliphatic compound that is on the right-hand side. We also work on a derivative from cardanol, which can be extracted from cashew nuts. So it's, I don't know, is the mouse, whatever. It's on the right-hand side, the one with the aliphatic chain and the aromatic ring. We are increasing the epoxy content to increase the mechanical properties, and we have done a huge work on epoxy vegetable oils in the scope of one previous project called AIRPOXY, in which we were able to design epoxy vegetable oil with very different content of epoxy, resulting from the different content in saturation. So we have these precursors, these epoxy building blocks, and then we work on their formulation to address some business case. So each time the idea is to tune the resin composition and to assemble all the precursor in order to reach first the process specification. So for instance, adapt the screwing cycles, adapt the performances, have the proper reactivity and stability depending on the processes. And then we address, depending on the project, this resin to different kind of application, mainly in aeronautic, automotive, construction, and energy. How we design our formulation? So as I explained already, we need to define the specifications that are linked to the implementation process. and the main performances that need to be reached when the material is cured. So it's aspects like viscosity of the resin, the curing cycle, the reactivity, gel time, post-life, what is the thermomechanical performances, and maybe in some cases you have some other properties that you want to put. So in terms of methodology, we always act the same. We want to define a petro-based resin that is a reference resin, which gives us the values that we need to target. We characterize this resin, and then we try with the bio-based or the sustainable alternative to make something that brings the same properties in terms of rheology or thermomechanical properties. We make the building blocks, we make the resin formulation, we make a pre-screening at lab scales, we evaluate the results, and then when we have the base candidate, we work for the pilot scale transfer and optimize the process to produce more quantities. So this is basically the idea for the bio-based part. So now if I go to the end of life of the thermoset and halates already presented everything this morning, but basically the idea is to work around dynamic and reversible networks. So there is different kind of approaches. It can be supramolecular dynamic networks, which is mainly a physical interaction. In our case, we are more on chemical interaction and associative cans, as it was explained already by Alex earlier. So if I focus on what chemistry exactly we are working on, so mainly three kind of chemistries: transesterification, transamination, and disulfide metathesis. So this is the three reversible chemistry what we are trying to put into building blocks in order to insert the building blocks into the materials, and then by the end of life use this reversibility to access to chemical recycling, reparability, and reprocessability, as it was done in the scope of AIRPOXY. To finish the talk, I just would like to say some word about three projects that we, past projects or projects that are ongoing, which really show all that I explained on our approach and methodology. So AIRPOXY project, in the scope of this project, the idea was to work with a combination of GEBA. I mean, the starting point was GEBA and a dynamic hardener from Sidatech. And our objective in AIRPOXY was to substitute the GEBA, and Caroline explained it was really important to find an alternative. And we developed these two molecules, so the one based on vanilla alcohol and the one based on fluoroglycinol, and working on these epoxies and on their mixture, it was possible to find an alternative to GEBA, which gives the same properties. In terms of TG, it was 130, the objective here, in terms of tensile modulus, and also in terms of impact strength. So this was really interesting. We figured out the best formulation to push further, and then we worked with the partners, and especially Sidatech, to evaluate the 3R properties. The results are here, and it shows whole aspect of the recyclability that are in the 3R. And also we worked with a tool manufacturer to produce the GEVA and the PhD at larger scale, and we were able by the end of the project to produce 30 kilograms of these resins. And it was used to make something like 40 demonstrators in the field of automotive. It was a panel for rear seat in Fiat cars. A word about Bison project that is ongoing. So it's still based on the Vitrimer approach, but in this case, the idea is to put chemistry into the materials that will help its degradation, but also help an enzymatic degradation step. So the starting point was if you put a thermoset material to an enzymatic degradation process. In this case, because the accessibility into the polymeric network is impossible for the enzymes will only act at the surface and the degradation will not occur properly. So the idea was to somehow have some reversible bonds to be broken by a chemical degradation process to somehow open a bit the materials and give access to the enzymes. So in the scope of this project, we addressed 4 different resins to epoxy, one I would say low TG, 80 degrees, one high TG at 205 degrees, one vinyl ester resin, and one unsaturated polyester resins. So the good news at this point of the project, we are at month 24, We found an alternative, reversible alternative to these 4 resins. And we are, for instance, quite happy to have a Vitrimer with a TG about 205 degrees with the other specifications. And now we produce this molecule. We also work on the degradation process, chemical degradation process, and now we provided the samples for the enzymatic degradation partners for further evaluation. So in the scope of this project, it was the same methodology that the one I explained about how we develop the resin in order to reach these objectives. And in Vibes project, so it's a project that is starting, I think, 18 months ago. It's still the same strategy, working on the reversibility. In this case, it's more geared toward composites. We are working on the resin, the matrix, designing building blocks that are dynamic, but also bio-based. So we try to design new building blocks that combine both aspects, bio-based and dynamic. So to make matrices, it's the same kind of matrices than the one before. And we're also trying to develop, I would say, sizing agents, even if I'm not sure of the term, that can bind onto the surface of the fibers, also have a reactive function with the matrix, and have in the center reversible bonds. The idea being we want to recover the fibers independently from the resin, and so break at the interface the linkages. So this is ongoing, but we are already working and at some interesting result on bio-based dynamic epoxies and hardeners. So to finish my talk, just to give you an idea of what would be the next step for specific polymers. So first, we would like to address more and more thermoset resins. So we are working on epoxies, on vinyl esters, and saturated polyester resin. As it was mentioned, it's important to address higher performance materials. And so we already reached 200 degrees TG, but there is some specification at 300 and maybe more. And so first trying to go bio-based on this part, but if we want to go on reversible and high performance, when I say high performance, I mean 300 degree TG, it will be difficult because of the chemistry of the reversible bonds. Then we want to widen our expertise in custom design on resin formulation, mainly trying to reach more and more properties and a wider scope of properties, and also improving our methodology. And for 4 years now, we are integrating a material modeling based approach in order to anticipate somehow the best idea we have in terms of material modeling. So it means putting the chemistry into a software and see what the software say in terms of property. We are not willing to have a predictive measurement, but just to have the main results, the main ideas, and then go experimentally in these areas. And finally, what we want to improve also is the scale-up part, because the solution we are proposing are low TRL solution, and we are conscious of that. And we need to strengthen supply chain, to work with other partners that can take what we have been doing at lab scale to bring it one day into the market. So I would like to thank all specific polymer team for their involvement in this area and these projects. I would like to thank Samuel Malburet, who is leading the material and environment activity and really participated to make this presentation. And thanks all of you for your presentation.